Okay, so the heights of women in the U.S. are normally distributed with a mean of 64. So immediately, normal distribution, mean of 64. And a standard deviation of 2.75. We're going to hang on to that. They're asking for the percent of women whose heights are between 64 and 69.5. So anytime they ask for a percentage between a certain interval or a proportion between a certain interval, it's a norm CDF question. So our minimum is going to be 64 up until 69.5, followed by your mean of 64 and your standard deviation of 2.75. So on my calculator, I'm going to hit second VAERS, norm CDF, 64, 69.5, 64, and 2.75. Get this. This is going to give me the proportion as a decimal, so 0.477, which, move that decimal place over, would be 47.7%. And it looks like our numbers are all rounded to the nearest whole, so that answer would be D. On number 2, which statements about statistical studies are true? A survey of all English classes in a high school would be a good sample to determine the number of hours students throughout the school spend studying. So you're kind of trying to look for, is there any bias involved there? Anything about the people that you're testing, English students, that would sway the number of hours students spend studying? And I don't think whether you're in an English class or not is going to sway or somehow make the results regarding how many study hours you put in. I don't think it's going to do anything to that. So that to me seems okay. We'll read the others and see kind of how we think. But number 2 says a survey of all 9th graders in a high school would be a good sample to determine the number of student parking spaces needed. That seems like a terrible idea because 9th graders don't drive. So what are they going to know about parking spaces? So I would get rid of that one. Number 3, a survey of all students in one lunch period in a high school would be a good sample to determine the number of hours adults spend on social media websites. Again, how do the people in a lunch period know anything about what time adults spend on social media? Seems very irrelevant. And 4, a survey of all Calc students in a high school who would be a good sample to determine the number of students throughout the school who don't like math. Okay? Going into a calculus class, if someone's even taking calculus, they're probably pretty decent at math, and therefore they probably like it a little bit more. So asking them would not be a good sample if you're trying to use your results to make a statement about all the students throughout the high school. That's not a good sample. That would introduce some bias because, again, those Calc students would probably be more likely to like math. So answer 1 is really the only one that's even remotely logical. Okay, number 3. Anne has a coin. She does not know if it is a fair coin, meaning fair coins have an equally likely chance of landing on heads and tails. If something was unfair, it might be weighted in a certain way. She doesn't know if her coin is fair. So she flipped the coin 100 times, and she got 73 heads. So she just physically, she did it once. She got 73 heads and 27 tails. She ran a computer simulation of 200 samples of 100 fair coin flips. So rather than redoing her 100 flips 200 times, she ran a simulation on the computer where in each simulation it flipped a fair coin. So the simulation was flipping fair coins. So it flipped a fair coin 100 times, and let's say it got this result, which was 30. The output is showing the proportion of heads, so that would be 35 heads. And then you could figure out the number of tails. And then she did another 100 coin flips, and she got, this maybe 0.38. She got 38 heads, and so on and so forth. And so there should be there should be 200 little dots here. So the average number of heads that they got were 0.497, so 49.7% of the time, which makes sense because it was the simulations were being done with a fair coin. Okay, but so here's how the 200 simulations were done. What she actually got when she did it with her physical coin, she got 73 heads. So the proportion of heads that she got was off the charts, meaning would have been if it had come up in any of the simulations, it would have been way up here. So that really means that 0 out of 200 simulations actually ended up with something that drastically off balance. So, given the result of her coin flip and of her computer simulation, which one of the following statements is most accurate? Her coin is not fair, okay? This was done by a fair coin, and you can see, and they tell you it was done by a fair coin, but that makes sense because it peaks around 50-50, which is what a fair coin should be. Granted, you can coincidentally get more tails than heads or more heads than tails, and that obviously can happen, but out of the 200 test trials, there was not a single time that with an actual fair coin she got something as high as 0.73 on her head proportion, which is what she physically got. So if 0 out of 200 simulations ended up there, then her coin is not fair. All right, Elizabeth waited for 6 minutes at the drive-thru at her favorite fast food restaurant. She was upset about having to wait so long and notified the manager. The manager assured her that her experience was very unusual and that it would not happen again. A study of customers commissioned by this restaurant found an approximately normal distribution of results. The mean wait time was 226 seconds, and the standard deviation was 38 seconds. So, approximately normal gives you the green light to draw a normal curve. The mean was 226 seconds, and the standard deviation we'll hang on to was 38. Given these data and using a 95% level of confidence, was Elizabeth's wait time unusual? So 95% is 2 standard deviations. So we want to go 2 standard deviations above, so that would be 226 plus 38 times 2. And we also want to go 2 standard deviations below, which will be 226 minus 38 times 2. So those two numbers, I'll just do those quickly, gives me 302 seconds and 150 seconds. So 95% of the time, people are going to wait between 150 seconds, which divide that by 60 seconds is 2.5 minutes. And 302 seconds divided by 60 seconds, just to turn it into minutes, is 5.03 repeating minutes. So 95% of the time, people are going to wait between 2.5 minutes and 5.03 minutes. Was Elizabeth's wait time unusual? Absolutely. 6 minutes is going to happen less than 5% of the time. So, yes. Yes, 95% of the time, people will wait between 2.5 minutes and 5.03 minutes. You don't really need that sentence because it does say justify, so this would have been good enough. You've shown all your math and where your numbers came from. But nonetheless, just if you want to really complete that, you can add that on. Stevens Beverage Company. Okay, Stevens Beverage Company is considering whether to produce a new brand of cola. The company will launch the product if at least 25% of cola drinkers will buy the product. 50 cola drinkers are randomly selected to take a blind taste test of product A, B, and the new product. 9 out of 50 participants preferred Stevens New Cola. Okay, so 9 out of 50 certainly is not the 25%. But keep in mind that that's just one sample. There's sampling variability. So maybe in their sample of 50 people, they just got unlucky. Could that have come from a population that was 25%? So the company devised a simulation based on the requirement that 25% of cola drinkers will buy the product. So each dot in the graph shown below represents the proportion of people who preferred Stevens' new product, each of sample size 50, simulated 100 times. So in their simulation, they assumed that the population would have a mean of 25%. Okay? And so, not unusual, the simulation of 100 simulations of taking 50 people from a population where the favorability is 25% produced a normal curve around a peak of 25%. We kind of want to see where this 18% fell, okay, which is obviously right here. So if you count out of the 100 simulations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 out of 100 simulations actually did result in something that low when the population did reach that 25% requirement. Okay, so 16 out of the 100 times, they did get unlucky enough to get something 18% or lower. So if that happened 16 out of the 100 times where they got 18% or lower, just based on luck, this could very well have been just based on luck. So assume the set of data is approximately normal. Does the sample proportion obtained from the blind taste test fall within the margin of error? So the margin of error is 2 times the standard deviation. So there's your standard deviation. So 2 times 0.0602 gives me 0.1204. So if you take, that's your margin of error. If you go off of your average, 0.25, by 0.1204, if you add 0.1204, you're at 0.3704, which is 37%. And if you subtract 0.1204, you're as low as 0.1296. So anything as low as approximately 13% or as high as 37% would be within the margin of error, and 18% was within that margin of error. So it is possible, and that 18% is within the margin of error to say, okay, that could still have come from a population with this at least 25% restriction. So the company decides to continue developing the product, even though only 9 out of 50 participants preferred its brand of cola in the taste test. Describe how the simulation data could be used to support this decision. So you could say, in the simulation, 16 out of 100 produced sample proportions of 0.18 or lower. Therefore, it's absolutely possible that the 9 out of 50 result was due to the coincidence of sampling variability, meaning the coincidence of who they happened to choose. They just got a little unlucky. Did I answer this question before? Does the sample proportion obtained? So the answer is yes. I did not answer that question. I need to actually answer it. Yes, and there's my justification. Okay, you can show that 18% does fall within there. Okay, number 6. Gabriel performed an experiment to see if planting 13 tomato plants in black plastic mulch leads to larger tomatoes than if 13 plants are planted without mulch. He observed that the average weight of the tomatoes from tomato plants grown in plastic mulch was 5 ounces greater than no mulch. So I'm just jotting down some notes there. The mulch was 5 ounces greater than no mulch. To determine if this observed difference is statistically significant, he re-randomized the tomato groups 100 times. So we know that the difference was 5 ounces. So we're looking for, and we'll say positive 5. It doesn't give us great info as to what average minus what they want, but mulch was 5 ounces greater than no mulch. To determine if the observed difference is statistically significant, he re-randomized the tomato groups 100 times to study these random differences in the mean weights. The output of his simulation is summarized in the dot plot. So when these plants were all shuffled by chance, and so these results are all due to chance, which should be centered at 0. And it's pretty close. How many of those are 5 ounces or greater? So 0, 1, 2, 3, 4, 5, 6. Okay, so this is probably 2, 4, 6, 8, 10. The scale's a little off, but 5 ounces or greater is right here. Okay, that's a good number of them. So in other words, this wouldn't be rare even if the mulch or no mulch conditions were there. So I would say that this 5 ounces very likely could have been due to coincidence, okay? Anything kind of within this range could have been due to coincidence. Unless something was, more than 20 ounces heavier or more than 20 ounces of a difference, I would say that it's not significant enough to say that it's just because of the mulch situation. Given these results, what is an appropriate inference that can be drawn? There was no effect observed between the two groups. That's a lie. There was an effect. The question is whether or not it was due to the mulch or not. There was an effect observed that could be due to the random assignment of plants to the groups. That is what I would say. Yes, we have an effect. It's a 5 ounce difference. But because this is kind of in the bulk of the graph, it's probably not due to the mulch as much as it's due to just kind of the coincidence of which group they were placed in. So I'm going to say this one. I'm going to read the other two just in case. There is strong evidence to support the hypothesis that tomatoes from plants planted in black plastic mulch are larger than those. No, that's not strong evidence. Okay, this 5 ounce difference was probably due to coincidence. It happened coincidentally a bunch of times here, if not more extreme by coincidence. So that 5 ounce is just not enough. There is strong evidence to support the hypothesis that tomatoes from plants planted without mulch are larger than those planted in. Same. Those are both out because the evidence is just not enough. This is too much in the coincidental area. It's only when we fall way out here or way out here in a simulation that we can actually suggest cause and effect. All right, last one here. So it's a pretty long-winded one. But we have Ava designed an experiment to determine the effect of a new energy drink on a group of 20 volunteers. 10 students were randomly selected to form Group 1 and 10 in Group 2. Each student in Group 1 drank 1 energy drink, and each student in Group 2 drank 1 cola. So they didn't label it here, but Group 1 is energy, and Group 2 is cola. So you don't have to keep reading that sentence. Each student in Group 1 drank, I got that. 10 minutes later, their times were recorded for reading the same paragraph of a novel. So question is, does the energy drink versus the cola make them read faster or not? So, hey.